So, let us continue with the earlier lecture. In the earlier lecture, we were talking about the big M method, where we have talked about the procedure and we have given one example. Let us see 1-2 more examples of different types. Earlier problem, whatever we have solved, if you remember, we have seen that there is no feasible solution, no optimal solution for that particular problem, because artificial variable was present in the final basis of the last iteration, and where all z j minus c j was greater than equals 0. That is one type of problem. Let us take the another problem. Let us see this one. Maximize z equals this, subject to this. Again, this is a similar type of problem which we solved in the last example. One less than equals type inequality, one greater than equals type inequality. That means, I have to add one slack variable for this first constant, whereas I have to subtract one surplus variable as well as add one artificial variable for the second constant. So, the given problem in the standard form can be written as maximize z, I am writing z later, subject to 3 x 1 plus 4 x 2 plus x 3 plus 0 into x 4 plus 0 into x 5, this is equal 6, x 1 plus 3 x 2 plus 0 into x 3 minus x 4 plus x 5, this is equals 3, and x 1, x 2, x 3 are x 1, x 2, x 3, x 4 and x 5 greater than equals 0. So, for this particular problem, your x 3 is the slack variable which you have introduced to make the less than equals type into equality type, whereas for the second constant x 4 is the surplus variable and x 5 is the artificial variable, by using which you are making the second constant of greater than equals type into equality type. So, in the objective function, it will be x 1 plus 5 x 2 plus 0 into x 3 plus 0 into x 4 minus m into x 5. So, as I have mentioned earlier, for the slack and surplus variables, the coefficient will be 0 in the objective function, whereas for the artificial variable x 5, the coefficient is a very large number m, and which is a negative coefficient minus m into x 5. So, therefore, your initial BFS for this problem will be, I have to make the original variables as 0, x 1 and x 2 as 0. So, if I put it on the first constant, it will be x 3 equals 6, whereas if I put in the second constant, in that case your x 2 is 0. So, that your x 5 will be equals to 3. So, in your this one, in your problem, your entering variable in the variables in the basis will be x 2 and x 3 and x 5. So, let us form the method from here. In the variable, you will have, just from here I am writing, your variables are x 3 and x 5. This will be a 3 and a 5. Value of c j, that is coefficient of the objective function corresponding to the decision variables, it is 1, 5, 0, 0 and minus m for x 5. So, here your c b, this is your a 3. So, it will be 0 and minus m. Now, let us write down the variables, that is 6 and 3. So, it will be 3, 4, 1, 0, 0 and 6 3. So, it was 1 3 0 minus 1 0. So, from the standard form, once you are writing it into this form, then as usual I will not waste my time here. I have to calculate Zj minus Cj by using the formula Cb into Xb minus Cj, which we have discussed earlier. So, it will be minus m minus 1, it will be minus 3 m minus 5, this is 0, this is m, this is 0. So, all Zj minus Cj not greater than equals 0 for all j. We have two negative numbers. Out of these two negative numbers, this one is the most negative. So, your entering variable will be x 2. So, corresponding to this column, I have to find out the ratio now, x br by y r j. So, x br by y r j will be 6 by 4 and 3 by 3. Therefore, minimum is 1. So, this is the outgoing vector and this will be your pivot element. Means in the next iteration in the simplex table in the basis, your x 5 will go out and your x 2 variable will be coming here, and I have to make this pivot element as 1 and all other elements in this column as 0. So, here now it will be x 3 and x 2. So, that this is a 3 and a 2 and your Cj remains the same. Please note this thing here, you have to note one point, that after this your outgoing variable or departing variable is the artificial variable x 5. So, once the artificial variable is going out of the system, then in the next iteration you remove the column corresponding to the artificial variable also. So, please note this thing, whenever one artificial variable is going out of the system, since due to the problem it is going out, then in the next iteration the variable corresponding to that artificial variable, that column also we will remove from our simplex table. So, that if you see the next table, here the column for x 5 we have removed, whereas it was present in the first table. The reason is the variable x 5 is artificial variable, and since it is departing, so I have to remove the corresponding column. So, now write down the Cj, that is 1 5 0 0. So, that your x 3 is 0 and a 2 is 5. So, I will make it 1. I am directly writing 1 1 by 3 1 0, that is 1 0 minus 1 by 3, and for this I have to make this as 0. For that one it will be 2 5 by 3 0 1 4 by 3. This I am not explaining, because already we have explained all these things in the last or earlier classes. The value of Zj again we are calculating in the same fashion. This is 2 3 0 0, but this value is minus 5 by 3. So, all Zj minus Cj are not greater than equals 0. Since all Zj minus Cj are not greater than equals 0, therefore, I have to go for the next iteration. So, only negative is this. So, this will be your entering vector. Corresponding to this, now I have to calculate the ratio. This will become 4 by 3 and this one 4 by 3 by 2. So, this will be 1.5. Here the ratio always must be non-negative. If it is negative, then we will not consider that particular ratio, because the ratio always must be greater than equals 0. Whenever we are explaining the mathematics behind simplex method, we discussed about this thing. So, once you have a negative ratio, that we will not consider. So, you have only one thing. So, 1.5, this particular row will go out. That means, the variable x 3 now depart from the basis and your entering vector is x 4. Now, x 4 will enter into the basis. So, that your this is the pivot element. That means, now I have to make this as 1 and this element as 0. So, in the basis now x 3 will be replaced by x 4, because that is the entering variable. So, let us see what happens. I am just keeping both over here, so that you can understand. Now, your x b will become x 4 and x 2. This will become a 4 and a 2. C j values remain same 1 5 0 0. Corresponding to this, the value will be 0 and 5. Now, from here you can directly calculate these values. I have to make this as 1 and this as 0. So, it will become 3 by 2, 5 by 4, 0, 3 by 4 and 1. This column is 1 and I have to make this one is 0. So, that R 2 minus something into R 1, 4 into R 1 plus 4 into R 1 will give you the result. So, it will become 3 by 2, 3 by 4, 1, 1 by 4 and 0. So, after this operation you will obtain the matrix like this. If you calculate the z j minus c j value, you will obtain 19 by 4, 0, 5 by 4 and 0. Now, you see here your z j minus c j is greater than equals 0 for all j. Z j minus c j is greater than equals 0 for all j, and z j minus c j is, I am just writing, is greater than 0 for non-basic variables. Your non-basic variables means which are not present in the basis, that is x 1 and x 3. Therefore, your optimum solution whatever you will obtain, that will be unique. Your optimal solution for this case will be unique, because z j minus c j greater than equals 0 and z j minus c j is greater than 0 for non-basic variables. And the solution is, in the basis only x 2 is present, x 1 is not present. Therefore, the optimal solution I can write down. Your optimal solution is, your x 1 is 0, since it is not present in the basis, x 2 equals 3 by 2 and your maximum value of z max will be, if you calculate, that is this into this C b into b, basically this into this plus this into this. So, it will become 15 by 2. So, this will be the solution of the problem. So, please note that earlier problem what we have done, for that z j minus c j, although it was greater than equals 0, but there was no solution, because the artificial variable was present in the basis. Whereas, for this particular problem we have z j minus c j greater than equals 0, artificial variable has been removed, and z j minus c j greater than 0 for non-basic variables x 1 and x 3, and optimal solution will be unique, and optimal solution can be written from this table itself like this: x 1 equals 0, x 2 equals 3 by 2 and z max will be 15 by 2. Let us take one more example, that is with equality sign, so that you can solve the problem by this: 2 x 1 plus x 2 plus 3 x 3 subject to x 1 plus x 2 plus 2 x 3 less than equals 5, 2 x 1 plus 3 x 2 plus 4 x 3, this is equals 12, and x1, x2 and x3 are greater than equals 0. So, this particular problem, if you see, one constraint is less than equal type and one constraint is of equality type. Usually, if you remember, what we have told is, for less than equal type inequality, you have to add the slack variable, whereas if it is greater than equals type, like earlier two examples, where you have to subtract one surplus variable and add one artificial variable. And if you remember, in the procedure we have told that if it is equality type, in that case you have to add one artificial variable only in the constraint to obtain the initial basic feasible solution. Let us see why it is required for this case. So, in the standard form, we can write it like this: maximize z equals, I will write down this thing, subject to x1 plus 2x2 plus x1 plus x2 plus 2x3 plus x4 is necessary equals 5, and 2x1 plus 3x2 plus 4x3, x4 will not be there. Say, suppose I am writing just like this, what will happen to this case? If I do not add any variable over here, what would be the consequence? As you know, to obtain the initial basic feasible solution, I have to make the original decision variables equals to 0, that is x1 equals 0, x2 equals 0 and x3 equals to 0. So, once I am making x1, x2, x3 equals 0, then I am getting x4 equals 5 here, but from here I am not obtaining any independent variable. So, for that reason, for equality I have to add one artificial variable over here, that is plus x5. So, that in the basis, if you have this one x1, x2, x3 as 0, then your x4 will be 5 and x5 will be 12 is the initial basic feasible solution. So, I am making 0 into x5. Now, what will be the form of the objective function? Original objective function is 2x1 plus x2 plus 3x3. As you know, for the slack or surplus variable, the corresponding coefficient of the slack of surplus variable in the objective function is 0. So, that you can write it as 0 into x4, and corresponding to the artificial variable x5, your coefficient will be one negative very high number, which we are denoting by minus m. So, that it will be minus m into x5, and x1, x2, x3, x4 and x5 all are greater than equals 0. So, I had the problem here. The problem is with this equality sign. Although this is equal, but I have to add one more artificial variable to this particular problem, because of what reason? To make or to derive the initial feasible solution. Here we are adding it. So, please note this one, that whenever you have the equality, sometimes if required to obtain the initial basic feasible solution, I may have to add one artificial variable, and the coefficient of the artificial variable in the objective function will be as usual minus m. So, your initial BFS basic feasible solution is your initial variables we are making 0, x1, x2, x3 as 0, and once you are making them 0, in the first constraint automatically you will be satisfied, x4 will be 5, and from the second one your x5 will be 12. So, effectively again I am emphasizing on this, that the way we are choosing our solution, that whenever we are starting, they always will satisfy all the constraints of the given problem, because they are satisfying the equality constant over here. So, either less than equals or greater than equals or equal type constant, if it is there, at least at equality it will be always satisfied. So, basic for initial BFS we are choosing in such a manner that from the very beginning itself it will satisfy the constraints. So, that our only problem will be to check whether the value of the objective function is optimum or not, and that we are checking by the value of z j minus c j value. If z j minus c j is greater than equals 0 for all j, then the value will be optimum. So, please note the beauty of the simplex method, that whenever you are starting your solution, you are choosing a particular solution in such a fashion that the solution will always satisfy your constraints. Only thing you have to check if it is optimal or not. If not optimal, again you will choose another extreme point of the feasible region, and extreme point means it will satisfy again the constraints, and you will iterate the process. So, now I will write down the simplex table corresponding to this particular problem. So, let us see this one. Yeah, now it is visible. So, your from here your basis, in the basis two variables x 4 and x 5 will enter. So, I am writing here your x b is x 4 and this is x 5. Here it is a 4 and a 5. C j values are the coefficients of the objective function, that is of the variables x 1, x 2, x 3, x 4, x 5 in the objective function. So, that it will be 2, 1, 3, 0 and minus m. So, C b value corresponding to a 4, a 5 is 0 and minus m. Your b values are 5 and 12. Now, write down these two constant rows, that is 1, 1, 2, 1, 0. Next one will be 2, 3, 4, 2, 3, 4, 2, 3, 4, 0 and 1. So, you are writing this. So, that is fine. Your standard problem now you have written in terms of the tabular form of the simplex method. As usual, calculate the value of z j minus c j using the formula C b into b minus c j. So, the value will be minus 2 m minus 1, minus 3 m minus 1, minus 4 m minus 3 and 0 and 0. So, z j minus c j is less than 0 for some j, most negative will come on minus 4 m. So, this will be your entering vector. Please note that on this side arrow means this is the entering vector. So, that your x 3 will be the entering vector. So, now you calculate the ratio, and minimum of these ratios will give you what will be the departing vector. So, in this case it is 5 by 2, and for this case it is 12 by 4. So, that your departing variable will be x 4. Your departing variable is x 4, and you have your pivot element intersection of this column and the first row is these 2. So, in the next iteration what will happen? Your f 3 will enter in place of a 4. So, that your b will be x 3 and x 5 will remain as it is. It will be a 3 and a 5. So, your c j is 2 1 3 0 minus m. Your x 3 is 3. So, it will be 3 and minus m. So, I have to make this as minus 1, sorry, this as 1 and this element as 0. So, as usual I am just writing the result directly, half half, this element is 1, half and 0. For this case, it will be 2, 0, 1, 0, minus 2 and 1. So, now calculate the Zj minus Cj. Your Zj minus Cj will be minus half minus m plus half 0 2m plus 3 by 2, please this will be 2m plus 3 by 2, this will be 0. Again we have a negative Zj minus Cj. So, this will be the iterative function. Effectively, I have to calculate also the this one x br by y rj. So, this is the entering variable, x 2 will be the entering variable. So, if I take the ratio, this will be 5, this will be 2. So, your x 5 is now going out, x 5 is going out, that is this is your pivot element. So, here if you see your artificial variable x 5 is departing at this second iteration itself. So, I have to go to the next iteration. In the next iteration, your x 5 will go out and x 2 will enter, and I have to make this element as 1, which is already 1, and this element I have to make as 0. So, I am writing this directly now. Your x b will become this one x 3 and x 2. So, that this is a 3 and a 2. Here if you note, in the earlier case, earlier table, artificial variable has gone out from this, and we have told once artificial variable is going out of basis, corresponding column of the artificial variable also should be removed, and we have done this one. Now, we are taking only 4 variables x 1, x 2, x 3 and x 4. Cj values are 2, 1, 3, 0, Cv values will be 3 and 1. So, after these operations, the columns will become 3 by 2, half, 0, 1, 3 by 2, 0, 1, 0, minus 2. Let us calculate the Zj minus Cj. I am not discussing all these things, because now I think you will be able to do it of your own. Again I have a negative Zj minus Cj. That means, again I have to go to the next iteration. So, x 1 will be the entering variable, for outgoing this will be there 3, whereas for this case this value will become 2, this v value will be 2. So, this divided by 0 is infinity. So, that also we cannot consider, therefore, only 3 is there. So, your outgoing variable will be now x 3. So, x 3 will go out and x 1 will enter. So, that in the next table your x 1 and x 2 will come. So, that this is a 1 and a 2, Cj values remains the same. Once the Cj values, that is it is 2, it is 1. Here the intersection of the row and column entering vector and outgoing vector is half, that is this is the pivot element. So, I will make as 1, this as 1 and the corresponding elements of that column as 0. So, if I make it, it will become 3, 1, 0, 2, 3, whereas it will remain as it is, already 0 is here. So, 2, 0, 1, 0, minus 2. If I calculate Zj minus Cj now, this is 0, 0, 1 and 2. Now, if you see all Zj minus Cj are greater than equals 0 for all j, and Zj minus Cj equals 0 for basic variables, Zj minus Cj is 0 for basic variables, Zj minus Cj is greater than 0 for non-basic variables x 3 and x 4. For non-basic variables, it is x 3 and x 4. So, for this case, the solution will become unique. Your optimal solution will be x 1 equals 3, x 2 equals 2, x 3 is not present in the basis, therefore, x 3 equals 0. This is your optimal solution, and value of z max will become now 2 into 3 this C b into b. So, 6 plus 2, that is 8. So, please note that since z j minus C j greater than equals 0 for all j and z j minus C j equals 0 for basic variables x 1 x 2, z j minus C j greater than 0 for non-basic variables x 3 and x 2. So, the optimal solution whatever you will obtain, that is unique, and optimal solution is x 1 equals 3, x 2 equals 2 and x 3 equals 0, and the maximum value of z whatever you are obtaining, this is equals to 8. So, I hope now you have understood how to solve the problems, LPP problems using big M method. So, in the next class we will start the what are the difficulties we may face whenever we will try to implement the big M method in computer, and what are the solutions or what are the other approaches may be available by which we can find out the solution of this.